Good day, everyone. So, today we shall be diving into quantities and units. And in this lesson, we'll be understanding the building blocks of measurement in physics, starting from fundamental quantities down to dimensional analysis of these quantities. All right, so let's start with the concept of quantity and unit. Now, when we say quantity in physics, is whatever you are measuring. Whatever you are measuring is referred to as quantity, such as length, mass, time, or even temperature. That which you measure is what we refer to as quantity. Now, how you are going to measure it is what we refer to as the units. How your measurement is going to be expressed. If you measure anything and there is no unit on that thing, that quantity will not make sense. It's only when a unit is attached to a number that is when that quantity will make sense. For example, now if you just say 5 alone will not mean anything except you put a unit like meters. When you say 5 meters, you know you are measuring the length quantity. If you say 5 kilogram, you know you are measuring the mass, the mass quantity. Okay. If you mention 5 seconds, you know you are measuring the time quantity, right? So every quantity must have a way it's being measured, and that's the unit. Okay, so these quantities are classified into two. We have the fundamental quantities and we have the derived quantities. Now, when we say the fundamental quantities, they are the independent quantities that other quantities depend on. Okay? They are the basics, physical quantities that other quantities depend on. And they are just 7 in number, as you can see them on the screen. They are not in any order. So we have the length, whose unit is meter. We use small letter m to represent the unit. We have the mass as well. This unit is kilogram. The symbol we use kg. We have the time, whose unit is second. Okay, we have the electric current, whose unit is ampere. We have the temperature, whose unit is Kelvin. We have the amount of substance, whose unit is mole. And we have the luminous intensity, whose unit is candela. And the symbol is CD. So each of these units have their symbols. Now, these units come in different form, okay? But the one that is being acceptable or the one that is being invoked now is referred to as International System of Unit or SI unit in French form. So all of these units you're seeing, they are SI units, okay? They are no longer, they are the one invoked now. No longer use the old form of unit to represent quantity. The SI unit is one that's invoked in our own 21st century. So the other type of quantity is what we refer to as the derived quantity, and the respective unit is called are called derived units. Okay, so the derived quantities are numerous, unlike the fundamental quantities that are just 7 in number, as you can see here. But coming to derived quantities, there are more than these that I have here. These are just some of the examples of derived quantities. Derived quantities are obtained by combining fundamental quantities. Okay, and derived units are also obtained by combining fundamental units. For example, now this is a derived quantity, area. Now, area can be, the formula for area is length times breadth. We know that length is measured in length, breadth is measured length is measured in meter rather, breadth is measured in meter as well. So length times breadth by unit to be meter times meter, so derived unit to be meter squared. Okay, so going forward to the next example of derived quantity is the volume. Volume formula is length times breadth times height. Length is measured in meters, breadth is in meter, and height is in meter. So if you put their unit there, that's meter times meter times meter, that will give you meter cube as the derived unit. So every derived quantity has its respective derived unit. Now for density, density is mass divided by volume. The unit of mass is kilogram. The unit of volume is meter cube, as we could see here. So the unit of density is mass kilogram per meter cube. Okay, because of the formula here. So we use the formula to determine the unit. Now you could see the way it's being expressed here: kilogram dot meter raised power minus 3. This expression is the same thing as when you express it in this form. When you express this, it can also be written like this. Now you can also have it as this. Now you can have kilogram per meter cube. Okay, it's the same thing with this here. It's the same thing. Okay, now you can see that the slash there has become raised to power minus here. That's actually different. So kilogram per meter cube or kilogram and raised to power minus 3 mean the same thing. Okay, there is no difference in the expression. All right. Now let's look at another one. The next derived quantity is the velocity. The velocity by formula is displacement divided by time, right? Displacement over time. Displacement is measured in meters, time is measured in seconds. So by formula, by unit, it will be meter per second or meter s to the power minus 1. All right. Then the next one is acceleration. Acceleration formula is change in velocity over time. So the unit is meter per second square. How do we arrive at this? Let's have an explanation to this. How do we come about this unit of acceleration to meter per second square? Very simple. You know, by formula again, we know that acceleration is change in velocity over time. So that means it means this is equal to velocity over time, right? And then we have seen that velocity unit is meter per second. Okay, so if we come here now, let's take it like this again. Let's say acceleration is velocity over time, that change velocity over time, and we have said that the velocity is meter per second, and it's going to be meter per second, and over time is also in seconds. Okay, now meter per second over seconds, if you do your mathematics well, they're going to be giving you meter per second square. This is how we came about this unit of acceleration to meter per second square. This can still be written as meter slash s to the power minus 2. It's the same meaning, same interpretation. Right? So then that of force, we could see the force formula is mass times acceleration. So if you do not know the formula for any derived quantity, you might not be able to get the unit. Now the unit for force is Newton. It has other units which can be derived from the formula. You go by the formula now. We say now that since mass is in kilogram, and then we now come here and put for mass. This is kilogram. Then times acceleration, we have just obtained acceleration to be meter per second square. So times meter per second square. So this will now be equal to kilogram meter per second square. So aside from Newton, another unit for force is kilogram meter per second square. All right, so we have so many of them. This is just um, a sample of derived quantities, some example of derived quantities. So we have other ones too that are obtained using this method too. Now, what are the differences between fundamental quantities and derived quantities? Let's start with their units. Fundamental units, they are standard units. Okay, the units are standard, they are globally accepted. But that of derived unit, the units are not really standard. They are formulated uh, from the fundamental quantities. Okay. Now, fundamental unit again form the basis of all measurement, but derived units are not the basis of all measurement. Derived units are obtained from fundamental unit. So, but fundamental units are not obtained from anywhere. They are just the basis. Just like if you want to learn your English language, your basis is to know your alphabet. So the alphabet for your physics subject is to know your fundamental quantities. Now we've said before that it is accepted by international organization, but that of derived unit is not accepted. Okay? And in a short form, we call fundamental unit SI unit. That is International System of Units. Why that of derived unit, we just call it units. Okay. So every difference you have in unit, you also have a quantity too. So fundamental quantities can stand alone. They have direct calculations based on this SI unit. But derived quantities cannot stand alone. They have to depend on fundamental quantities. All right. So these are the major differences between fundamental quantities and derived quantities with their respective units. Okay, there's another aspect of physical quantity that we need to talk about, and that is dimension of physical quantities. We have looked at fundamental quantities and derived quantities, but then we also have the dimension part of it. The dimension part of it just describes how these quantities are related to three major quantities: that mass, length, and time. And one distinct difference between dimension and um, fundamental quantities is that we use capital letters to represent dimension. For example, now mass. The unit of mass is kilogram. But when you talk about dimension, we use capital M to represent mass. The same goes to length. The unit of length is meters. But when it comes to dimension, we use capital L. So when you are asked to get dimension, let it not be mixed up with the unit of these quantities. Okay. So for mass is capital M, for length is capital L, and for time is capital T. All right. But in some cases too, we use I for current or capital A for current. Okay. Where we use theta for temperature. But those two cases are very rare. All right. So now let's look at dimension of some quantity here. Look at density now. If you don't know the unit of a quantity, you might not be able to get the dimension. Now density, if I want to take us back again to what we have talked about earlier on, if you look at it, say density here by unit is kilogram per meter cube. Now this is the unit of density. Now if I know the unit of density, it will be easier for me to get the dimension. Now this is the unit of density now. If I now want to compare it with its dimension, so let's see this one. Now the dimension of density now is ml per minus 3. How did this come about? Very simple. Since I already know that by unit, the unit of density is kilogram kilogram per meter cube, right? So with this now, all I need to do is to substitute the symbols. For dimension, we know that whenever we say kilogram, we use capital M as That's for mass. Whenever we say meter, that's my we use L. So L raised to the power what? Minus 3. That's just it. So the dimension for density is ml raised to the power minus 3, while its unit is kilogram and meter, kilogram per meter cube. Alright? That of velocity also, remember that the unit of velocity is meter per second. Right? So we know that it is meter per second, meter per second. Now, applying the dimension, the meter is represented with capital L in dimension, while second is represented with capital T. So T raised to the power minus 1. Okay, so that is the dimension for length, dimension for velocity using the units. And that of acceleration too. So we know that the unit of acceleration is meter per second square. Automatically applying it to dimension, the meter there become capital L. Second is capital T to the power minus 2. So that's it here. All right. That of force to the same thing applies. If you apply that rule, you'll be getting dimension to be this ml to the power minus 2. Right. So are how these are the way you express physical quantity in a dimensional way. So let's see one or two questions, jump question. Look at this question here. It says the international aggregate system of units for physical measurement are we have IB, FT, second. Okay, so this this option A is not it, okay, because we don't use this anymore. We don't use feet. We don't use feet again. Second is still in vogue, okay, but we don't use feet. We don't use them this particular symbol to represent mass. We use kilogram, okay. We use kg. We don't use IB. We use kg. Option B, we have gram, meter, and second. So SI unit, we don't make use of gram anymore. We make use of meter, we make use of second, but we don't make use of gram to measure mass. Okay, it's actually this symbol is representing mass, length, and time. Okay, so we don't use this to represent the unit of length, mass, and time anymore. The third option, we have kilogram, meter, and second. Yes, so the third option is correct. Fourth one is saying cmg and second, it's not correct. The correct answer is C, kilogram, meter, second. Okay, we have another one here. This one is let's go to question 8. Question 8 is more related to what we are talking about. So here we have for which of the underlisted quantity the derived unit correct. Okay, now this is option. We have I, the moment of a force. I we have work. I we have acceleration. So which of them is correct? All right. Now, for you to know if it is correct, you must know the unit of all of this quantity mentioned here, right? Okay. So let us start with the first one, moment of a force. Moment of a force formula is force times distance. Okay, force times distance. Now, what is the dimension of force times distance? Let's quickly solve that. So let's start with moment of a force. So moment of a force, we have moment of a force to be force times distance, right? And then we know that force dimension is m l t to the power minus 2. Then times that of distance is l because it's length. Now if we bring these two together, we have l times l will give us l squared, and then we have t to the power minus 2. Now if we come back to the question here, which one is equivalent to it? So we have this. This is correct. So this is ml squared 3 to the minus 2. So moment of force is correct. That of work also is force times distance. So moment of force and work have the same formula. So work formula is also force times distance. Definitely it has the same dimension. Then the third one, which is acceleration. Of course, we know that acceleration dimension is L t raised to the power minus 2. So the only ones that are equivalent to that dimension given here are I and I, that movement of the force and work. So that will give us, let's look at the option that had I and I as the correct answer. That is option D. Option D, as you can see here. So option D is the correct answer for this question. Question 9 says, which of the following is not a fundamental quantity? Okay, A, which is meter, is fundamental. B is ampere, fundamental. C is Kelvin, is fundamental. D is second, fundamental, because meter is for length, ampere is for current, Kelvin is for temperature, second is for time. The last one there, which is radian, is not fundamental. So E is not a fundamental unit. All right. So we are going to be drawing our curtain here. Thank you for listening and have a wonderful rest of the day. Bye for now.